A mathematician looks at a sandwich and, instead of having lunch, decides to make life difficult for the whole of humanity. Because a normal person sees bread, ham, and thinks, good, food. A mathematician sees something else. A question. An unnecessarily dangerous question. Is there a cut capable of splitting all that exactly in half?
So far, one might say, well, it is not that dramatic. We take a knife, cut more or less through the middle, and get on with our lives. But no, because mathematics, when it has the chance to make an everyday situation strange, does not miss the opportunity.
The real problem begins when someone says, yes, but let us imagine that the sandwich has completely fallen apart. The top slice of bread is on one side, the ham is all crumpled somewhere else, the bottom slice of bread is twisted, shifted, deformed, as if it had had a bad afternoon. And even so, mathematics asserts that there is a single flat cut that can divide half the amount of one slice of bread, half the amount of ham, and half the amount of the other slice of bread, all at the same time. Not a more or less cut, not a cut by eye, not a cut that says, well, it is fairly even, let us not be too intense about it. An exact cut.
This is the Ham Sandwich Theorem. And yes, that is what it is called. It is not a nickname invented by the internet. It is not the desperate strategy of a teacher trying to stop their students from falling asleep. It is not the title of a lost episode from a children's series. It is a real theorem, a serious one of those that appear in books on geometry, topology, and measure theory. But it has the name of an afternoon snack, and that already makes it rather wonderful.
Because, let us be honest, one expects the mathematics studied in earnest to have intimidating names. Something like the fundamental theorem of the spectral representation of compact operators, which, from the outset, makes you reconsider your life choices. But no, here we have a sandwich. Bread, ham, and a knife. And, of course, an idea which, beneath this domestic image, is far deeper than it appears. Let us imagine the scene in a much simpler way. We have a nice plate, a ham sandwich. It is made of 2 slices of bread and a slice of ham in the middle. If everything is neatly assembled, cutting it in half seems easy. You lower the knife and that is it. Nobody calls a topologist for that.
But now, let us imagine a more realistic scene. The sandwich has fallen apart. The bread has shifted, the ham is folded irregularly, with one part sticking out beyond the bread. Perhaps someone has even squashed it a little. Perhaps it was carried in a backpack, leaving it in a rather sorry state. The question is, can we still make a cut that divides each ingredient exactly in half?
The answer given by the theorem is an emphatic yes. There always exists at least one cut. And here I have to make an important clarification, because mathematics has that habit of being very precise while also ruining nice-sounding phrases. The theorem does not say that there is a unique cut. There may be several. There may be a great many. What it guarantees is that at least one exists. That, which sounds like a tiny technicality, is fundamental. Mathematics is not saying this is the magical cut, the only one, the one chosen by the destiny of Ham. No, it is saying something more sober, but much deeper. No matter how disordered the situation may seem, at least one balanced cut must exist. And that is already strange. Because let us think about it for a moment. Intuition tells us something else. Intuition tells us that if everything is a mess, if the sandwich is scattered or deformed, the most likely thing is that one cut will balance one thing and ruin another. You cut the bread properly, but all the ham ends up on one side. And if you correct the cut for the ham, now the bread is uneven. You adjust the top slice of bread, but the bottom slice mocks you from the other end of the plate. It is the kind of problem where one thinks, there is no way this works. But mathematics says, yes, it does. Not because you can see it, not because it is easy to find, but because by the structure of space, that cut has to be somewhere. And that is the interesting part of the matter. The Ham Sandwich Theorem is not a cookery recipe. It is a statement about balance. It says that in our three-dimensional space, three measurable objects can be divided simultaneously in half by a single plane.
Yes, you are right. I had better translate that into everyday language. If we have three things with volume, for example, 2 slices of bread and a slice of ham, there exists a kind of flat cut that can split the three quantities in half at the same time, even if they are arranged oddly, even if they are off-centre, even if they do not form the sandwich of a Michelin-starred restaurant, even if it looks like a snack assembled by someone with no patience whatsoever. As long as we can measure how much there is of each thing, the theorem comes into play.
And now, yes, how about I tell you the story behind this appetizing result? Because this idea, with its food-related name, was not born in a kitchen. It was born in one of the most intense mathematical environments of the 20th century. We are heading to Lwów, the most important city in western Ukraine. In the 1930s, it was part of Poland and was an extremely important intellectual centre. A group of mathematicians worked there who would later become known as the Lwow School of Mathematics. My apologies for my dreadful pronunciation.
Now, when I say school, I am not thinking of a building with pupils copying in silence. Quite the opposite. Strange as it may seem, we have to imagine cafes. Yes, cafes, with cups of coffee, cigarettes, a rather unhealthy habit, admittedly, endless discussions, and one detail that is not minor at all: marble tables. The mathematicians spent hours sitting in those places, jotting down ideas, discussing problems, and writing formulae directly on the marble table. Do you see why I emphasise that?
The most famous place of all was the Scottish cafe. No, it was not a cafe full of bagpipes, kilts, and blue flags. It was a cafe in Poland in the 1930s. Today we can see the building, although now, as far as I understand, a hotel and a restaurant operate there. But in those days, the Scottish cafe bore that name, and that name became forever linked to one of the best-known legends in the history of mathematics. Major figures gathered there, and as their names appear, if you are mathematics students, theorems will begin to come to mind. Stefan Banach, Hugo Steinhaus, Stanislav Ulam, Stanislav Mazur, Julius Schauder, among other brilliant mathematicians. Sometimes they met for hours, sometimes for days. They proposed problems to one another, they challenged one another, they discussed solutions. And when an idea occurred to them, they wrote it on the marble tables. This had one advantage. The tables served as improvised blackboards, but they clearly had one rather obvious disadvantage. At the end of the day, someone cleaned the table. Can you imagine the drama? A mathematician spends hours thinking. He finds an idea, he writes it down, he discusses it. Perhaps he goes to sleep convinced that he is close to solving an important problem. And the next day, an efficient waiter, doing his job perfectly, has erased a possible proof from history. For anyone else, only a clean table remained. For them, that clean table embodied a scientific tragedy. That is how the famous Scottish book appeared, a notebook in which they began to record problems, solutions, conjectures, and challenges. It is said that Banach's own wife provided the notebook. The book was kept in the cafe, and the mathematicians kept adding their questions to it. And here is a story I love. Some of the questions that remained open had prizes attached, and the prizes could be very serious or rather absurd. A bottle of wine, a dinner, a coffee. But one of the prizes was extraordinary. A live goose. But let us regain our composure. The mathematics being developed there was not only abstract, it also had something of a club, a wager, an endless after-dinner conversation, a kind of let us see if you can solve this. with consequences which, as we have seen, could include poultry. It is in this world that Hugo Steinhaus appears. Steinhaus was a very important Polish mathematician with a special ability to find problems that were simple to state but difficult to solve. The sort of problem that anyone can understand in 2 minutes, but which then demands deep tools. And I think you will agree with me, the Ham Sandwich Theorem fits perfectly into this category, because the question is almost ridiculous. If I have 3 things in space placed in any way whatsoever, can I cut them with a single plane and divide all 3 in half? The truth is that it does not sound like a monumental question. It sounds like something that occurs to someone who has been staring at a charcuterie board for too long. But that was Steinhaus's talent, to see a deep mathematical structure beneath an everyday image. The first known solution is attributed to Stefan Banach, and Banach was not just some person passing through the cafe looking for pastries. He was one of the great mathematicians of the 20th century. His name appears in fundamental results in modern analysis. All of us who have studied mathematics have come face to face with Banach spaces, with the Hahn-Banach theorem and with the Banach-Steinhaus theorem. And yes, Banach is one of those surnames that, in mathematics, is not there for decoration. But in this story, we find him linked to a problem with the name of a sandwich, because Banach solved the problem, and he did so by using a tool from topology related to the Borsuk-Ulam theorem. Do not be alarmed. The aim of my account is not to enter into the technical proof, because I am not here to turn a sandwich into torture for those not well versed in mathematics. But it is worth understanding the intuition behind it. The Borsuk-Ulam theorem has a very famous popular version. It states that at any moment on Earth, there are 2 exactly opposite points that have the same temperature and the same pressure. Do you see it? 2 places on the planet, each directly opposite the other, sharing certain values. The underlying idea is that when something changes continuously, certain coincidences become inevitable. But of course, you may be wondering, what does that have to do with our poor sandwich? Let us think about the knife, or better still, let us think about all possible knives. A cut can be more tilted, less tilted, higher, lower, more rotated towards one side, more rotated towards the other. There is an enormous number of possible ways to cut. Now, for each orientation of the cut, we could move the plane until it divides one of the ingredients properly, for example, one of the slices of bread. Then we look at what happens to the other slice of bread and to the ham. Perhaps there is too much ham on one side. Perhaps one of the slices of bread is shifted, or even squashed on one side. But if we change the orientation of the cut, those imbalances change as well. And at some point, by continuity, a position appears in which those imbalances cancel out. Put plainly, if as we move the knife, the error changes sides, then at some point there must have stopped being an error. Incredible, isn't it? I bet you had not thought about the matter in that way. It is like when you are trying to find the right temperature in the shower. First it comes out freezing, then it comes out boiling. If the tap is not possessed, at some intermediate point there has to be a reasonable temperature. Well, with far more abstraction and far less shower, the idea has something of that about it. Balance appears because it cannot fail to appear. That is the magic of mathematics. We do not need to see the cut. We do not need to know how to find it by hand. The theorem tells us it is there. Somewhere among all possible cuts, it is there. Wonderful, isn't it? But this story does not remain in that Scottish cafe, because Europe was about to break apart. The Second World War destroyed the world in which that mathematical community had flourished. The city that housed the Scottish cafe was occupied, changed hands, and many lives were split forever. Some mathematicians managed to emigrate, others met the worst possible end, others survived in extremely harsh circumstances. The focus shifts to the United States. In 1942, the British mathematician Arthur Harold Stone and the American John Tukey appear there, working together. and they publish a paper entitled Generalised Sandwich Theorems, generalising that old Ham Sandwich Theorem.
What is it about? Well, Stone and Tukey took the idea to a broader form. It was no longer only about 3 objects in our everyday space. It was about a general rule. In 2 dimensions, 2 things can be divided by a line. In 3 dimensions, 3 things can be divided by a plane. In 4 dimensions, 4 things could be divided by something we can no longer picture properly, but which plays the same mathematical role, and so on.
There is no need to imagine a 4-dimensional sandwich. In fact, for the sake of mental health, it is better not to. The important point is that Stone and Tukey transformed a concrete image into a general tool. The sandwich stopped being merely a sandwich and became the friendly way of telling a much more complex idea: how to divide several quantities in a balanced way with a single cut.
And now comes the inevitable question, one that those of us who teach hear so often in the classroom. Does this serve any purpose, or is it just a mathematical oddity with good gastronomic marketing?
Of course it serves a purpose, but I have to admit it is not that in everyday life someone takes out a ruler, invokes Banach and cuts a cake in a state of topological trance. It does not work like that. Theorems do not often appear in daily life with a flashing sign. They appear as underlying ideas, as ways of thinking, as models that inspire methods for sharing out, organising, separating, or balancing.
Let us begin with a first example. It is a birthday, and the cake appears. A cake with cream, chocolate, and strawberries. The strawberries are not evenly distributed because the person who decorated the cake clearly had a special sense of aesthetics. There is one area full of strawberries and another where barely one landed, seemingly out of sheer obligation. If we cut the cake through its geometric centre, perhaps the 2 portions have the same amount of sponge, but one keeps almost all the strawberries. And then the family conflict begins, because someone always looks at the other person's plate, always. Which would you prefer? The portion with more strawberries? The one with fewer strawberries? Or why not, the portion with no strawberries?
The Ham Sandwich Theorem helps us think about this kind of problem. It is not enough to divide just one thing. Sometimes we want to distribute several quantities at the same time. Sponge, cream, strawberries, chocolate. In the ideal model, we can look for a cut that balances more than one feature at once. In practice, of course, the cream sticks to the knife, the cake tilts, someone complains, and an aunt says she only wants a tiny piece, but then asks for the most loaded one. Mathematics cannot deal with that. But it does show us that sharing fairly can be much subtler than cutting where the centre seems to be. I propose a second example. A pizza. Let us think of a pizza with mozzarella, olives and ham. But all the olives are on one side because someone threw them on with enthusiasm and little strategy, or perhaps it was the result of a delivery mishap. If we make a simple cut, one half may look like a complete pizza and the other like bread with a memory of cheese. So the question is no longer, how do I cut the pizza into 2 equal areas? The question is, how do I distribute the toppings as well? The theorem, in its ideal version, pushes us to look at the distribution of quantities, not just the outer shape, because 2 halves may be the same size and yet be profoundly unfair. This applies to pizzas, to cakes, to sandwiches, and, unfortunately, to many human gatherings.
Let us take another example. Suppose 2 people inherit a field. Not a perfect field from a school textbook, but a real piece of land. Irregular, with one more fertile zone, one part with trees, another near the water, and another that seems to have been designed exclusively to generate legal disputes.
If the land is divided into 2 parts of equal area, that does not mean the division is fair. One person may keep the best soil,
and the other a collection of stones, wind, and resentment. So a similar idea appears. We do not want to divide only area, we want to balance resources: fertile land, water, access, and value.
The Ham Sandwich Theorem does not automatically solve a legal case, nor does it replace a surveyor, nor does it prevent the heirs from blocking one another on WhatsApp. But it offers a powerful mathematical image. A fair division may require balancing several things at the same time. Now, let us leave the kitchen and the field. Imagine a city full of points on a screen. Each point may represent a delivery order, a school, a sensor, an aerial, a patient, a business, or a bus stop. If we want to divide the city between two work teams, it is not enough to draw a line through the middle of the map. Perhaps almost all the orders end up on one side and almost none on the other, which will create a great inequality. Just ask the team that ends up running around like mad to deliver all the orders, while the other team is busy watching the World Cup soccer match. In computational geometry, problems of this kind are studied: how to divide points, regions, or data in a balanced way. The classical Ham Sandwich Theorem is not always used literally, but it belongs to the same family of ideas: cutting space, separating sets, balancing quantities, and organising chaos. See? What began with an appetising sandwich of bread and ham ends up leading to birthdays, pizzas, data, maps, algorithms, and the distribution of work. That is how fascinating mathematics is. If you enjoyed this story, please subscribe to the channel, leave a comment, and give me a like. This is Histarmat: history, art, and mathematics.